Yep.
What kind of latencies are we talking about? And
Yeah, good question.
Kind of compensation?
Right. This gets into sort of perceptual stuff. What's a perceptual latency? The kind of main metric is, can the DJ talk and not go crazy hearing himself back? Actually, some of them like that, but it's actually you don't want to have a delay that's that audible. And so the tightest spec that anybody really expects to happen is about 10 milliseconds, which is not that hard to do in this case. But with IP, particularly with a multiple link system that's gone through and back and forth a few times, you can get beyond 10 milliseconds after a couple of passes through a link. So again, the links, there isn't a fixed length. It depends on how much is going on in that network node at the time, and how many channels, and so there's a lot of variables there. So you want to take a worst case, kind of you have a scenario for a worst case, and make sure that you stay below 10 milliseconds. So they try to make the single link average latency down below 1 millisecond. So you can get like a 10 link path and still be below that, essentially the cutoff being that live DJ or live anybody listening to themselves, live musician, and 10 milliseconds is that barely the earliest edge of perception. In fact, AES, A to D converters have latency too, and so we've been living with latency for a while, and in anything that's digital, anything that went after we left the full end-to-end analog path, there was latency. And so there's also trade-offs in how you design it. You shorten latency, you can create phase shift, so you want to balance all that out. In the A to D world, they've learned that the hard way over the years. But there's always been some level of latency, and mostly it's tolerable. It's only when it gets beyond into that, past the 10 millisecond. The other place where latency creeps up is in these data compression systems, MP3, that kind of stuff. That adds a lot of latency because it has to process sound in blocks, and it has to wait for the block to build up. And so you get a fair amount of latency there. Luckily, we're in an uncompressed domain typically in the pro space nowadays, luckily, thankfully. And so we don't have to worry about that. But there's all kinds of latency in the STL links. Sometimes those RF links between the studio and the transmitter, those may be the last place where there's a compression, data compression being used. So sometimes that's the worst case for the latency. And so if you want to listen off the air or the transmitter itself, well, HD radio, unfortunately, has a 4.5 second latency. So you can't listen to off the air anymore in digital radio. So people have given up on that. So they just listen to program locally. But that's where you want to try to keep that. And if you stay under 10 milliseconds total aggregate, you're fine. In fact, most people don't hear even 20, but 10 is usually considered the limit, and that's the target they go for. Another one?
In the world of, I guess, like higher sample rates, and especially with like studios that are doing like full orchestras with like, like really high sample rates, like 196 and stuff. Is there any issue of running into problems with 1,000 bass, like your gigabit?
Well, I mean, you could do the math, and at some point there would be. Is that the question again? To repeat it is, what about high-res digital signals, 192 sampling, 24-bit depth, that kind of thing, and many channels of that? Do you max out a link? And of course, at some point you would, if you do the numbers. You can see the numbers are pretty ridiculous before you would do that. But if it were necessary, just run another cable. And as long as the switch is really the place where you would most likely run out of space, because it's got to be dealing with everything that's going on in the facility at once. There may be that one orchestra recording all those high-res things in one place, but you may have 7 or 8 little rooms all doing 2-track editing or assembly post stuff. and they all have to add up, and the switch has to be able to handle all of that. So it's that aggregation point where it all comes together that you're first concerned about. And this kind of stuff is telcos, the whole telecom industry lives with that all the time. They know, and that you have to deal with scalability, and that's the whole basis of the IP. The Internet Protocol was designed to be able to accommodate that in a fairly smooth, seamless way and just be able to build and grow. And, it was amazing. They had no idea how popular it was going to become when they did it, and yet it still manages to deal with it. Now, they decided that we're going to run out of IP addresses with IPv4, so that's why they have IPv6, which is a even longer address, and they have a migration path to get from the old addresses to the new addresses, and that, but again, we're not close to running out, but they're already thinking ahead. So here you could do, it's the same thing that you would do in this case. Figure out what your sampling rate's going to be, what your per channel, bandwidth's going to be, and do the numbers and see whether you first of all need 100 base T or gigabit, and if maybe you need multiple gigabit paths for one particular room. But again, in this world, we're not dealing with that in the broadcast space, but you might in the pro audio space. So that's where the next level is, and how you accommodate that is going to be, I think, where a lot of these systems move to next, and come up with practical solutions. It's certainly possible to do. It's just how you can make them cost effective and easy to implement and operate with. All right. Hey, well, thanks for sticking around. Appreciate it. All right. Thank you. Thank you.